Welcome to the Problemers channel season 3 episode 5, the episode which I titled Euclid Says, because in this episode we will evaluate a certain trigonometric sum using the machinery of synthetic Euclidean plane geometry. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material presented on this channel is for you to go to the home page of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you, use the comment section, and I will do my best to find the time to answer all of your questions. The objective of the mathematical problem S3M4 is to find an alternative expression for a finite trigonometric sum shown over here on the board in front of you, where we sum the values of the trigonometric function of cosine evaluated at the arguments that form an arithmetic progression in the form of a plus k times theta. The numbers a and theta are real, and k is the summation index in that case. It is a non-negative whole number that varies between 0 and n is evidently also non-negative whole number, which we take to be fixed, 0, 1, 2, 3, 4, 5, 6, 7, and so on. The summation runs with the index k starting with the value of 0 from 0 to n, and in this case we are looking for a way to compress that finite number of terms, the finite number of sums, into a certain product. Even though we do not really have to go with the product, we can leave it as a difference of certain terms. And if you are a casual internet straggler who just happened to come across this episode, then by working through the material that we present in this episode, you will definitely learn something meaningful, interesting, and tangible, because it is the case that will happen every time you watch anything on our channel, because this is who we are and what we do. With every episode on this presented on this channel, you have a chance to learn something interesting, meaningful, and tangible. But for best results, we recommend that these 3 episodes, season 3 episode 5, this episode, season 3 episode 4, and season 3 episode 3 are consumed as one in a sort of a transaction, because across these 3 episodes, for the first time on this channel, and from that point onward we will do it quite often, we come face to face with the idea that fixing a given technical problem, let's say in mathematics, and then trying to generate, construct, and then synthesize as many distinct enough solutions of that fixed problem as you can muster, should be an integral part of the fabric of studying and doing mathematics and physics and computer science. And to that end, in season 3 episode 3 shown over here, we actually evaluate this here sum using nothing more than the middle school arithmetic of the standard and basic popular trigonometric identities, but we do it by exposing the fact that the sum shown over here can be morphed into a sum that possesses a tactically advantageous property of telescopicity. We explain what a telescopic sum is in general and how to work with the sums, and we carry this idea through in season 3 episode 3. In season 3 episode 4, we use the basic arithmetic of complex numbers shown over here. This is the wonderful identity that combines three functions in one neat package. This identity is due to a Swiss-born mathematician, Leonhard Euler, who published this result, if I'm not mistaken, in 1748. And we take this idea through and show how to fold this sum in terms of complex numbers shown over here. And one more time, in season 3, episode 3 here, we use nothing more than the middle school arithmetic. There is nothing beyond a typical, in my time, middle school curriculum in, let's say, in mathematics. Here with complex numbers, we do not really use anything super fancy that requires you to know something at the college level. So this is thoroughly, let's say, lower to middle high school material shown over here. And in this episode today, in season 3, episode 5, we will use the so-called synthetic Euclidean plane geometry in order to investigate the plausible underlying plane Euclidean geometry of that sum. And the word synthetic means that we will do so without the introduction of any coordinate system or any machinery associated with the so-called analytic geometry. And we will show how to evaluate this sum using Euclidean plane geometry, appealing to nothing more than our favorite right triangles and a couple of properties of a circle. In order to hone in on a plausible Euclidean plane geometry interpretation of our two favorite sums by now, we will make a straightforward but temporary simplification, which in a way we will cancel and come back to original sums over here. And to that end, we recall that again in season 3, episode 3 and season 3, episode 4, using middle school trigonometric identities on the one hand and the basic arithmetic of complex numbers on the other hand, we already established that for our finite sums shown over here, the trigonometric function of cosine shown on top in red, the trigonometric function of sine is shown in green on the bottom, but we understand what this notation means. It's these functions taken one at a time. The argument to both of these functions is one and the same. We already showed that an alternative expression or representation of that sum as a product is given over here, and the only difference between these two representation across two functions, cosine and sine, is the multiplicative term over here that sits in front of the ratio that are actually one and the same in both cases shown over here. And for the sum of cosines, this ratio is multiplied by the cosine. For the trigonometric functions of sine, this ratio is multiplied by the sine. The argument to these functions is always one and the same, a plus n theta over 2. Here's the thing. In physics in general, this is a problem too. In mathematical modeling of various real-life phenomena, this is the case too. And in mathematics, evidently, that is the case too. Sometimes in order to understand, to wrap our brain around something that seems to be complicated, we come up with a simplified model. And sometimes that model can be quite crude, but amazingly enough, sometimes it is the case that even simple or a very crude model still affords a very, very deep and meaningful understanding of the underlying phenomenon. And this is the case in this situation. So as a temporary simplification, we do the following maneuver. First, we cancel out this constant real number a in these formulas for both of the sums uniformly all the way across. We say a is equal to 0. Now, in this case, for the sums of the trigonometric functions of sine, when the constant real number a is equal to 0, evidently here we will have for the argument sine of k theta, where k varies from 0, and we know that when k is equal to 0, k times theta, or 0 times theta, is 0. The value of the trigonometric function of sine evaluated at 0 is 0. So these two notations over here, when we start the sum from 0 and we start the sum from 1, Basically, they make no difference. Adding 0 to a real number does not change it. So in some sense, on the one hand, we can keep it like that, but just to be consistent, because with the underlying geometry, things are very sensitive to which numbers we use. So we will roll our sum with 1 for the sign, but then nothing else on the right hand side of this equality changes in any substance. Substantially, it's pretty much the same thing. We simply erase or eliminate a at 0. And what I did over here, if you notice, I moved the sign from the numerator of the ratio in the front over here, and then when a is equal to 0, sine of n theta over 2, I moved it back into the numerator over here. We will understand why very quickly. It is not that complicated. For now, it may be mysterious. Yes, why did Roman do it? Well, Roman did it because it is needed for the storytelling purposes, and we will see that this swap is really not that significant. And the elimination of this number a is also not significant. It does not affect really the essence of what's going on. But like I said, it simplifies the model to the point where we can wrap our brain around it, see what is going on, and then we complexify it back to crank it up to the original level and take it home all the way with this expression that was given. And since this manipulation for the trigonometric functions of sine is very straightforward, the manipulations for the trigonometric function of cosine are a tad more involved, and we carry them out as follows. With the trigonometric functions of cosine, the situation is actually quite similar, and just only a tad involved, and in some sense we can leave it as an exercise to the reader. So here is a look at that manipulation in an expedient manner, mostly for a reference with the correct response. Our sum of the trigonometric functions of cosine, now evaluated at the argument k theta, where k varies from 0, can be represented which way? Well, naturally, when k is equal to 0, the first summed, the value of the trigonometric function of cosine at 0 becomes 1, plus the rest of the sum, which is the sum that starts with 1, as I showed over here in red. It is in a small font, but you guys should see it. It's 1. K starts from 1. And from this, it follows that that sum that starts with 1 is equal to, carry over here, is what? This sum minus 1. This sum minus 1. This sum over here, we know what it is. From that expression, we simply erase a, set a to 0, and then we have our cosine of n theta over 2 times our popular ratio. We saw it already twice, the sine of n plus 1 over 2 theta in the numerator, and in the denominator, the sine of theta over 2, the trigonometric function of sine, minus 1. What do? Back to middle school. We bring the whole caboodle under the common denominator, which is the sine of theta over 2. And what does that mean? Well, from this product, we subtract 1. From this product, we subtract 1. Technically, game over. We go back to this middle school trigonometric identity. Sine of x times the cosine of y minus cosine of x times sine of y, these guys, is equal to the sine of x minus y. And here what do? Well, look at this. We set x equal to n plus 1 over 2 theta, which is this argument right here. X is the argument of sine. And we set y equal to n theta over 2. This is this guy. Y, x. What is x minus y? Well, x minus y, this difference erases n. We have n over 2 theta minus n theta over 2. Gone. What is left? Theta over 2. So the difference is theta over 2. And what is x minus y in this case? Well, it's this guy right here, theta over 2. This is this guy. So here we take the two terms that are nearest to the equal sign, and we rotate these terms about the equal sign. Carry the sign with the minus sign to the left-hand side of the equal sign, and this product, cosine x times sine of y, with the positive sign, to the right hand side of the equal sign, and voila, we write down this is exactly what we have in the numerator over here. And what do we have for this expression? Cosine of x, which is n plus 1 theta over 2, cosine of n plus 1 over 2 theta, times what? Sine of y. What is y? Y is n theta over 2. Sine of n theta over 2 divided by the denominator, and the game is over. Essentially, that is all there is to it. Now we take these two sums over here, this sum and this sum. We take these expressions over here, and we basically come up with a plausible explanation for the sums using the machinery of synthetic Euclidean plane geometry as follows. Because I went through this exercise several times already, I realized that the best way to present a plausible geometric interpretation of the finite trigonometric sums at hand is to first prove the following useful lemma. We will refer to it as lemma 1 for the lack of a better name. The setup in this lemma is the following. Let sigma, shown in green, be a circle, also shown in green, centered at the point O with the radius r. Everything is non-trivial. R is greater than 0. R is greater than 0. And let A, B, C be 3 distinct points shown over here in red, A, B, and C, chosen on the circle sigma in such a way that the distance between the points A and B is precisely the distance between the points B and C as reflected over here. The distance AB is equal to the distance BC. If you guys can distinguish colors, I hopefully showed these line segments of equal length in red. If you cannot distinguish the colors, then look at double ticks. Double tick, double tick. Look at this and then realize what's going on over here, and let the straight line AB be extended in such a way that on that extended straight line AB we pick a distinct point D in such a way that according to the axioms of plane geometry due to a German mathematician David Hilbert, the point B is in between the points A and D, and the point B is chosen on the straight line AB extended in such a way that the magnitude of the angle CBD and DBC can be meaningfully defined, and to that angle what we refer as theta. This is precisely the angle theta in our finite trigonometric sums that we will meet in a few seconds. And under these conditions, the claim of this proof, the claim of this lemma is the following. The magnitude of the central angle AOB, which I temporarily designated with x, is actually equal to the magnitude of the angle theta. Think about it. Use this as an opportunity to practice mathematics correctly, as I explained in season 1, episode 2. Put this video on pause, walk away, think on your own, try to generate your own proof. But our proof will be very short. It basically amounts to a very short angle chasing. And angle chasing is a term that is used in the Olympic mathematics, and it amounts to locking onto a given planar geometric situation, picking up some amount of angular material, and then literally chasing one angle after another until we arrive at a needed conclusion. What is the conclusion here? Well, look at this. The magnitude of the angle ABD, the magnitude of the angle ABD is equal to pi radians, simply due to our constructions. This is how we constructed our setup, and that means from this it follows that for the magnitude of the angle CBA, what do we have? Well, it's the magnitude of the angle ABD, which is pi. From that angle we subtract the magnitude of the angle theta. In other words, pi minus theta equals CBA. A. That's on the one hand. On the other hand, what do we have? On the other hand, we have two triangles that are isosceles. Why are they isosceles? The triangle AOB and the triangle BOC are both isosceles, and they're actually both congruent by what? By S, 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 side, side, side. The length of the side AB of the triangle AOB is equal to the length of the side BC of the triangle BOC. And all the following lengths of the sides AO, BO, and CO equal across these two triangles because they represent the radius of the circle. Sigma as such by SSS, these two triangles AOB and BOC are isosceles, and by, if we go back to our favorite Euclid's Elements, Book 1, Proposition 5, this is the famous Pons esse norm. According to that proposition, the magnitudes of the interior angles at the base of each and every non-degenerate planar Euclidean triangle that is isosceles, every isosceles triangle, must be equal one another. In other words, the magnitudes of the angles OCB, OBC must be equal one another. They're shown with beta. And the magnitudes of the angles OBA and OAB also equal one another, and they're also beta. And as we just proved, the triangles, these triangles, isosceles triangles, are congruent, so all the angles shown in beta are really reflect the mathematical truth in this case. And what does that mean? That means that on the other hand, the magnitude of the angle CBA can be represented as what? As two copies of the angle beta. Exactly, as two copies of the angle beta. That's on the one hand. And what do we have on the other hand? Well, this is another elementary observation. Let's do it this way. Book 1, Proposition 32. It's easy to remember. 32 is a perfect power of 2, and two right angles make what? Two right angles, pi over 2 plus pi over 2. 2 times pi over 2 is pi. According to this proposition, the magnitudes of the interior angles actually of any non-degenerate planar Euclidean triangle sum to pi radians. So from here, what do we have? From the triangle, which one? A, O, B, what do we have? We have x plus 2 beta is equal to pi. Would you agree? This is basically the manifestation of Book 1, Proposition 32. The magnitudes of the interior angles in any non-degenerate planar Euclidean triangle sum to pi radians. X, beta, beta, x plus 2 beta is equal to pi. AOB is non-degenerate Euclidean triangle. 2 beta is the courtesy of the fact that the triangle AOB is what? Isosceles, exactly. From here, it follows what? That x is equal to pi minus 2 beta. And now what do we do? Pi minus, what is 2 beta? Pi minus theta. So minus pi minus theta. You see, open up the parentheses. What do we have? Pi minus pi plus theta. You see, typical middle school angle chasing manipulation, very short. Pi and pi cancel each other out. What remains? Theta. So what did we prove? We proved that the magnitude of the angle theta, x, is none other than our favorite angle theta. So the angle AOB by magnitude is actually the same as, let me use the same color, is actually the same as the magnitude of the angle BOC. And that magnitude is what? Theta, 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 shown right here. And this is exactly what we were set out to prove. And now we use this fact, keep a mental image of this diagram over here, because we will construct our geometry, if you will, a plausible geometry of our finite trigonometric sum precisely using this setup shown over here. And we will do that as follows. We begin our construction process with a single right triangle V0, V, V1, V0, V, V1 for vertices. In such a way, this triangle is constructed in such a way that the magnitude of the interior angle at the vertex V is pi over 2 radians. The angle is right, and importantly, the length of the hypotenuse of this and all the consequent triangles is still 1, the positive unit. In other words, the distance between the points V0 and V1, V0 and V1 is precisely 1. Let me write it down over here, guys, as one of our basic assumptions. V0, V1 is equal to 1, positive unity. Then, based on the middle school definitions of the trigonometric functions, and this is why I use the word plausible for a plausible geometric demonstration, because these definitions only work for triangles where the magnitudes of angles, interior angles, vary only in a certain way. But in general, of course, in grown-up mathematics, the trigonometric functions of cosine, sine, tangent, and cotangent, and all the happy family is usually defined in terms of power series, which is an infinite series over the set of real numbers over the set of complex numbers. So here is the limitation just to trigonometry of right triangles. In such triangle, based on the definition of these trigonometric functions via the corresponding right triangles, what can we write for the length of the line segment V0V? V0V, this length is what? Is the length of the line segment V0, V1, V0, V1 times the cosine of the angle 1 theta. And we precisely pick the magnitude of one of the interior angles of such a triangle to be 1 theta. As you guys guessed already, there will be more such triangles, and the angle here will be exactly 2 theta, 3 theta, 4 theta, and so on. But based on the middle school definition of the trigonometric functions via the corresponding right triangles, we have for the length of the line segment V0, V, this expression over here, because the length of the hypotenuse in this triangle is 1 times the value of the trigonometric function of cosine evaluated at the angle 1 theta, is basically numerically this trigonometric function as if it is sitting here all by itself. And in the complementary fashion, for the length of the line segment V, V1, V, V1, what do we have? We have the length of the hypotenuse V0, V1 times the value of the trigonometric function of sine evaluated at the argument 1 theta. The length of the hypotenuse V0, V1 is 1, the positive unity. 1 times the sine of 1 theta is precisely, again, the sine of this angle 1 theta. So geometrically, see, this is the important bit to realize early on, that geometrically we already represent our terms of the given sums as line segments. Blue line segments, let's say, for cosine, and red line segments for the sine. And now the idea is basically to take, remember, our sum of cosines was basically what? Cosine of 1 theta plus the cosine of 2 theta plus the cosine of 3 theta, and the same thing for the sines. The sines was the sine of 1 theta plus the sine of 2 theta plus the sine of 3 theta plus so on, plus and so on. And the whole idea behind a geometric interpretation of this here finite sums, and then rolling these sums back into A plus, where A is not 0, is to linearize all the sums, or I'm sorry, all the terms, all the summands in these sums. And what does it mean to linearize them? Linearize them means to represent each algebraic, if you will, term in this sum geometrically with the corresponding line segment, and then try to stretch all these line segments into one favorable large line segment where we can extract some tactical advantage from this linearization. So basically, linearization sounds fancy, but it's very, very straightforward. In a few seconds, we will construct several such triangles, and then we will see that the linearization means tag these line segments that represent each algebraic sum end to end, and thus represent the algebraic sum geometrically. This is all there is to it, and we'll do the same thing for the sines. And the essence of this piling on line segments that represent our sums is the following. Again, I suggest that you guys use this as an opportunity to practice mathematics correctly, do the right thing, as we explained in Season 1, Episode 2. Put this video on pause, walk away, and try to answer the following 2 questions on your own. Compare your ideas to ours. Maybe you'll come up with a better idea. Hopefully you come up with a better idea. First question, what is the shape of the second triangle that we're about to construct? And the second question is, how do we place that second triangle whose shape you just constructed with respect to the first one? Meanwhile, my idea is the following. Again, if you have a better idea, share it with our community in the comment section. The second right triangle should have exactly the same length of its hypotenuse. Let's say the second triangle will be named V1, V2, something else, whatever you want to name that point over here. The interior angle at that point will be the magnitude of the interior angle at that vertex of the second triangle will be again pi over 2 radians. The length of the hypotenuse is 1, but the way we construct / position that second triangle is it follows. Bringing back the material from our Lemma 1 that we just proved a few seconds ago, we can extend the straight line V1, V0, V1. Remember, in our lemma it was AB. We extended as shown over here with a dashed line. And then if we carefully construct a straight line that is either perpendicular to V1, V, shown in blue here, or parallel, this straight line parallel to the straight line V0, V, it doesn't really matter as long as this angle over here is right. Then with respect to that straight line, this blue straight line over here, this extended green hypotenuse over here will form which angle? The angle theta. Theta, evidently, of course, yes, because basically what we're doing here is we're translating and then again shifting, do composition of 2 translations, and we basically position this triangle over here from the vertex. We move vertex V0 into V1, slide our triangle, let's say that way, and voila, we have the line segment V0V parallel to this line segment over here, and we're pretty much done. Then here is how the whole thing works, and this is why it is important to understand what is the mechanics of the second triangle, because once you understand it, you're in. You should be able to carry the computation through. You do not need me. You can finish this whole thing on your own. So here, with respect to our first green hypotenuse of length 1, V0, V1, we incline the second green hypotenuse of the same length 1 by which angle? Theta. Exactly. You see, this is our angle theta from the lemma, and we already understand that the circle that is lurking over here, the central angles with that circle will be precisely theta. And once we do that, the magnitude of this interior angle at the vertex V1 of the second right triangle will be what? Well, as I showed over here, it will be 2 theta. And if we play the same middle school game of defining our favorite trigonometric functions of sine and cosine via the corresponding right triangles, for this line segment, the blue one, we will have what? Numerically, cosine evaluated at the angle 2 theta. And the vertical red line segment will have the length of what? Numerically, it will match the value of the trigonometric function of sine evaluated at the angle 2 theta. You see, this is how straightforward that is. I, of course, expanded, blew up the things a lot. This is very aggressive. In a few seconds, I'll erase this and I'll use much smaller triangles to construct the whole picture for you guys. But it is important to realize that this is the basic of the little engine that could. Once you understand what's going on here, you can expand it to n triangles and n terms on your own without any problem. So before, in the previous segment, I used the fancy term linearization of the terms. Well, the algebraic terms of our finite sums, we correspond to line segments of the appropriate length. You see, this is how the geometric interpretation of our sums works. To the algebra, we attach geometry, and conversely, to a given geometry, we attach the algebra, and thus the algebra and the geometry enjoy a mutually symbiotic relationship. So what is this linearization of the terms? Well, look at this. We now, maybe even I use this guy. We technically, the words that you will have to say when you write up your presentation is the following. We project orthogonally the blue line segment here that represents the second term in our sum. We project it orthogonally onto the straight line that sits over here. You see this straight line. And once we do that, let's say I'll do it by hand, guys, you understand. Once we project orthogonally, so we will have what? This line segment over here will represent precisely the value of the trigonometric function of cosine evaluated at the angle 2 theta. And what does this line segment from V0 to here will represent? This bad puppy right here, what will it be? Well, that will be precisely the geometric interpretation of the sum of the first two algebraic terms, cosine of 1 theta plus cosine of 2 theta. You see, this is it. Then what do we do? Well, in the final picture we'll project these things even further, but here we again orthogonally project the line segment V1V, this guy, orthogonally onto the straight line extended for the side of the second triangle. See, this way. So this guy goes this way and this guy goes this way. So this distance right here will be what? Well, this distance will be sine of 1 theta, you see, and from here to here, from this point to this point, so this distance right here will be what? Well, this will be a geometric representation of the algebraic sum of the first two terms, sine 1 theta plus sine of 2 theta. Once you understand this, so here it will be, let's say, plus, we brought this down, cosine 2 theta, and brought it down technically means, if your professor asks you, what does it mean to bring it down? Orthogonal projection of the line segment from one place to another over here on this straight line. What is orthogonal projection? Orthogonally project every point. Every point is projected in the orthogonal fashion. So the line segment here, the blue one that represents cosine of 2 theta, is faithfully carried down, if you will, or represented by this line segment over here, exactly the same length. And now we have a geometric interpretation of the algebraic sum, cosine of 1 theta plus cosine of 2 theta. This is the horizontal, if you will, projection and representation, and this will be vertical representation, sine of 1 theta plus sine of 2 theta. So here, if you will, and I don't really have that much room, but you guys understand, this way all the way up to here. See, so this is what it means when I say linearize the terms. Stretch them end to end into one straight line. See, cosine of 1 theta, boom. Cosine of 2 theta, boom. In the next triangle, cosine of 3 theta, cosine of 4 theta, and stretch them end to end into one line segment. The same thing will happen with the vertical stretching. They will have sine of 1 theta, sine of 2 theta, sine of 3 theta, and on and on and on. But we know all along there is a circle lurking over here with a favorable and advantageous central angle. Like once we connect all these, there will be central angle theta, theta, all over will be theta, and then we'll have one interesting line segment that will connect all these points, and voila, we will be pretty much done. And this is what will happen if we tack on n right triangles, as I explained above, one on top of the other, and project the corresponding sides of the smaller triangles onto a proverbial horizontal and onto a proverbial vertical. If you understood how we constructed the two right triangles that we explained how they work with one with respect to the other in the previous two segments, then you will understand what I constructed over here. This is basically the previous two triangles, this triangle and this triangle. But these two triangles on drugs, basically, they ate a lot of good mathematics and then they grew into a larger chain. But essentially, the underlying mechanics are exactly the same here as were in the previous segment, except that I scale things down a lot to show you guys what happens when the number or when these right triangles start growing like mushrooms after the rain. The first triangle with the interior angle theta, the second triangle with the interior angle 2 theta, the third triangle with the interior angle 3 theta, the next one and the next one, the kth triangle with the interior angle of k theta, and the last, so to speak, triangle with the interior angle over here n theta. I did not show the helper straight line, which is the extension of the hypotenuse of length 1 into this one, because it's going to be too messy as it is. But I suggest that you use your favorite software construction tool to experiment with this. I use GeoGebra. So basically, at first I play with GeoGebra, then I construct this contraption over here. And again, what do we see? We see that we project orthogonally all the cosines or all the sides of our smaller triangles that correspond to the values of the trigonometric function of cosine onto the perceived horizontal over here shown in blue. And likewise, we project all the line segments that are shown in red over here that represent the values of the trigonometric function of sine on the perceived vertical shown over here. And because these projections take their origin, let's say, at the first right triangle, it should be evident that the horizontal straight line, which collects or absorbs all the, let's say, algebraic terms, cosine of 1 theta, cosine of 2 theta, and so on, cosine of n theta, and the perceived vertical that absorbs the values of all the trigonometric functions of sine, sine of 1 theta, sine of 2 theta, sine of 3 theta, and so on, sine of n theta. These two straight lines intersect at what angle? Exactly, they intersect at the point P at right angle. So in other words, the magnitude of the angle V0 P Vn is equal to pi over 2. You see, this is important, pi over 2. And look at this. By value, we know algebraically, if you will, or analytically, the magnitudes or the values of the trigonometric function of cosine decrease as the angle grows. The trigonometric function of cosine is gradually decreasing, and as that happens, the sine, the values of sine, increase. So look at this. Large cosine of smaller angle, small sine of smaller angle. But as the angles grow, our cosines shrink, and that is represented geometrically. The length of the corresponding line segments gets smaller, smaller, and smaller. But the length of the line segments, each of which represents what? The trigonometric function of sine, they get progressively larger. Look at this. This one, this one, this one, this one, and the larger one. So we project horizontally all the blue, let's say blue line segment that represent cosines onto a horizontal. We project all the red line segments that represent the sines onto the vertical straight line. We glue these line segments end to end. This is what exactly the operation which I refer to linearization. We stretched all these. Before, they were our line segments that represented the cosine and the sine. They were in some weird zigzag step ladder formation, not very convenient to act on. But once we project them on the corresponding straight lines, we stretch them end to end, we linearize them, we stretch them into one straight line, which is the aggregate total for all these terms represented analytically, if you will, or algebraically. And what do we have now? Well, I will take a short break, but for you guys, it's a small quiz. If our sum of cosines, shown over here, is represented what? By the length of the line segment V0p from here to here. This is the sum of our cosines. And if the sum of our sines of k theta is represented by the length of the line segment VNP, this guy, and the angle between these straight lines V0p and VNP is right, is pi over 2, in order to deduce the alternative expressions for our sums, because in a way we already solved the problem, we just do not know it yet. But in order to represent these guys in terms of the locally available material, what would your next maneuver be if you were to solve this problem that way? We recommend that you put this video on pause, walk away, think on your own, then come back and compare your ideas to ours. One winning maneuver over here is to connect the points V0 and Vn. As I showed here, the vertices V0 and Vn with one orange colored line, because now we have what? We have a number of things going on. We have a right triangle V0P Vn with the magnitude of the interior angle at P that is equal to pi over 2 radians. This is a right triangle on the one hand. On the other hand, the line segment V0Vn is what? It is the proverbial base of an isosceles triangle V0OVN. And that triangle, isosceles triangle, why is it an isosceles triangle? Well, because now that we stretched all our geometric representations of the algebraic, if you will, or analytic terms of our sum end to end, which means that we tile these line segments as shown over here, the horizontal one and the vertical one, tight with no gaps and no overlaps, we see that the vertices V0, V1, V2, V3, and so on, they sit on our circle sigma, as we showed earlier. They belong to one and the same circle. How can this be seen? Well, take, for example, the 3 points V0, V1, and V2. These are 3 distinct points. They always define 3 distinct points in a plane, determine a unique circumcircle. How do we construct it? Well, bisect one side, bisect the other, boom, the point where the 2 bisectors intersect produces such a circle. But if we move these 2 sides, this and this, we step right, so to speak, and look at the same triangle with the vertices V1, V2, and V3, it is essentially the same triangle. It's congruent to the first one, but it shares the side, this one, with the first one. And the angles over here, the interesting angles, are all the same. The lengths of the sides are the same. The triangles are congruent, so it can be shown that this perpendicular bisector and this one will also intersect over here, so we have a circle. And with our line segment V0Vn, the arc, the circular arc that this line segment spans or subtends, the angle V0OVN, is by construction how many? N copies of the angle theta. So what can we say now once we introduce this successful, it was a happy idea to connect the vertices V0 and Vn? Well, now we go back to our middle school definition of our favorite trigonometric functions. And what do we have for V0? For the length of the line segment V0p. It is equal to what? To the length of the line segment V0n. it is V0 Vn, Vn times the value of the trigonometric function of cosine evaluated at what angle? Theta plus, let's call this angle right here, this angle over here, we'll call it x. Theta plus x, and what do we have for the length of the line segment PVN for, well, let's say VNP. This is this sum right here. We have exactly the same length of the same hypotenuse, V0 Vn times the value of the trigonometric function of sine evaluated at the angle theta plus x. Now, what do we do with this angle x? Well, look at this. Now we go back to the theory of circles. For those who are interested in his elements, Euclid develops the theory of circles in book 3. So here, look at this. Our angle theta we already have, but what about angle x? This guy right here, the angle x. It subtends, look at this, one hypotenuse over here, our line segment V0n. So it subtends the circular arc, which one? That runs from Vn. From V1 to Vn, this guy right here, see, one less angle. And what do we know about the angles in the circumference? Well, the corresponding central angle is twice the angle in the circumference. So the corresponding central angle, which is this guy right here, this one, and this is what? This is n minus 1 copies of the angle theta. So what do we have? Let's say over here, n minus 1 copies of the angle theta is equal to what? Twice this angle right here, guys, this angle. If this is confusing, so let me erase this. The angle theta is here. And this guy is angle theta, this guy right here. So n minus 1 theta, this is the central angle, this one, is twice the angle in the circumference because it subtends the same circular arc, Vn. V1 equals to 2x. From here, x is equal to n minus 1 over 2 theta. And what does it mean? So now we say theta plus x. So x, where should I write it, guys? Where should I write it? Let's say right here. Well, let's do it this way. Theta plus x is equal to what? N over 2 theta minus theta over 2 plus theta. Theta minus theta over 2 is plus theta over 2. So here this sum comes out to n plus 1 over 2 theta. Would you agree? This is all that there is to it. So now we rewrite these two functions as follows. I'll just erase and you guys understand where this came from. But now we have n plus 1 over 2 theta, and this is n plus 1 over 2 theta just as well. You see, already our terms that we recognize from our previously discovered alternative expressions for these sums, they already emerge. But now we have this one guy, the length of the line segment V0 Vn in terms of the locally available material. How can we compute it? Well, it is very straightforward. Remember, the triangle V0 O Vn is what? It is isosceles. So for the length, let's say for the length of V0 Vn, what do we have? If this is r, if r is the radius of this circle, sigma, on which our vertices of this right triangle sit, it is, again, not even funny how straightforward that is. It is equal to 2 times r times the value of the trigonometric function of sine evaluated at where? How many copies of the angle theta we have here? Exactly n. So we have our n theta over 2. Bam. Done deal. And what can we say about this twice r? How can we recover it? Well, we go back to our atomic unit of manipulation, if you will, our very first triangle. The length of this hypotenuse is 1. This is r. So how can we express this 1 and r, knowing that the angle here, the magnitude of the internal angle in this isosceles triangle, v0, o, vn, is theta, and the length of the side is r. It is r here and r here. Well, let's do it this way. I'll write it over here. 2 times r times sine of theta over 2 is equal to 1. Would you agree? 2r projected onto 1, theta over 2 gives us 1. This follows from this triangle, v0, o, v1. Game over. So now we have 2r, but we take 2r from here. You see, this is the connection right here. This is it. So here, from this formula, I'll take a few seconds right now. I will erase this. I'll short break. But you will see in the next segment, in a few seconds, we will see what? 2r is equal to 1 over sine of theta over 2. We put it over here. Take v0, v1 over here, and we're done. And all we have to do now is carefully write down the result of our geometric observations. Remember that in the previous segment, using the fact that the triangle V0, O, V1 is isosceles, the length of the sides of this triangle are R, the radius, and then projecting these sides onto the base, which is of length 1. We obtain this relation. We put this 2R into our formula for the 2r times the sine of the angles and theta over 2 for the base, for the length of the base v0, vn, and voila, we realize that the length of this line segment v0, vn is precisely given by this, because here we basically 1, there is 1 lurking over here. 1 is the unit of length of the base of this isosceles triangle, and the game is over. We go back to our expressions for the sums of cosines and sines, and by using our geometric representation, remember that we represented our analytic or algebraic, if you will, terms of these sums with the corresponding line segments, which we tiled, which we bunched up, and we connected them end to end, and we tiled the corresponding line segments tight with no gaps and overlaps. Cosines live on a proverbial horizontal, sines live on the proverbial vertical, tight, no gaps, no overlaps. All the angles everywhere where we care, they are right. The whole thing worked, and now this is our result. The sum of cosines represented this way, and their sine, the sum of sine is represented this way. And for those of our viewers who stayed with us and worked through this episodes as we recommended, we go back to the end of season 3, episode 3, the first episode in the sequence. Remember, at the end of that episode, I posed a couple of thought-provoking questions for you guys. How can we explain what the first question was? Where do all these half of the angles come from? 1 half, 1 half, 1 half, 1 half, here, and what is the peculiar? The second question was, what is the peculiar feature in the structure of these formulas? Well, now we understand that these halves, 1 half, 1 half, 1 half, 1 half, basically are the bisectors, the angular bisectors of the corresponding isosceles triangles. That is all there is to it. Here, the bisector of the angle theta is the fact that this is how we recovered the length of the circle, the length of the radius of the circle on which our vertices sit. This is 1 half from here, and these guys and this guy, the halves over here, come from the fact that when we computed the angle that was subtended by the arc V1, Vn, this one, and the length of the arc from Vn to V0. This is all there is to it. In the first case, for the circular arc Vn to V1, we came to over here. Remember, This is the angle. If this is confusing, the angle theta plus angle x. This is the remnants over here in this term. This is our angle. You guys see what's going on. I'm about to mess it up, but this is the angle. Bam, this guy right here. Theta. This angle is theta plus x. Remember, this is x. And this is where we got the half from, because the circular arc VN V0 spans in this implementation, or in this situation when k rolls with 1. How many? Exactly n copies of the angle theta. One less is n minus 1, and so on. And this is where the halves come from. There's basically the angular bisectors of the corresponding isosceles triangles that live on the corresponding circle. The small isosceles triangle and the large isosceles triangle, and this is it. So now in this ratio, remember in the previous episode when we dealt with complex numbers, this ratio, I named it rho, and it popped out almost naturally from the complex numbers woodwork. Why is it one and the same? Well, that is because it's one and the same line segment, V0, Vn, multiplied by cosine to produce the sum here, the blue sum, the horizontally, and exactly the same line segment, the length of exactly the same line segment, multiplied by sine to produce the vertical line segment. Game over. This is the explanation of this beautiful relationship where we basically, the sines and cosines project one and the same line segment, the base of the isosceles triangle VNOV0, onto the corresponding horizontal and vertical. Horizontal for the cosines and vertical for the sines. Game over. So in some sense, maybe for some of our viewers, these formulas now have fairly transparent geometric representation. And look, here we did not use any coordinate systems. That is why in general we can refer to it as synthetic Euclidean plane geometry. And now the next question, now that we understand what is going on in this perhaps the most simple case where we roll the sum with, I left the room, guys, specifically to say from 1, we roll the sums from 1. We now start cranking things up. Instead of rolling the sums from 1, we now roll them from 0. And once we understand how that works, we will throw in another, the initial angle, if you will, 8 plus k theta. And in the next segment, you guys don't have to, you can skip forward if you're not interested in it. But in the next segment, I'll consider the case when k runs with 0. K runs with 0, and that means we basically step over here one more time this way, see, and we jump over here. We still have our radius here, but this time instead of I don't know which joke. So here, let's say it will be a green one, still a green line. It will come over here. This will be the point. See, when we roll with 0, then what happens when we roll our sum with 0? Well, sine will have no contributions. It's 0. But here we will add precisely 1. And this, the extra, this is precisely 1. This is how wonderful things work out. The cosine of 0 is 1. And this is essentially what we do to our contraption, is we add one line segment of length 1. And what will happen? Well, instead of V0, we'll have the point. Let me call it V minus 1, for example. So instead of this line segment, we'll construct it starting from here. This line segment will run this way. But then the underlying arithmetic, the underlying geometry will still be the same. We will have the angle in the circumference, which is 1/2 of the corresponding central angle, and the arithmetic will work out in exactly the same way. And for those of our viewers who want to compare their work to ours, this is how this computation will unfold. Here at this stage, when we considered our sum starting from the value of the summation variable 0, k equals 0, k equals 0, things get a little messy. I apologize, but you guys should understand what is going on. Once we add the line segment of length 1, and that corresponds to us rolling our sums from k equals 0, not from 1, but from 0. In the first case, we produce a contribution of what? Cosine of 0 is 1, a line segment of length 1, this is this guy. And in the second case, the contribution is what? 0, and that's exactly what we have with the line segment of length 1. On my drawing, it looks hopelessly not correct, but in reality, this line segment will be in this line over here. Think about it, guys. So this line segment will be along this horizontal line that carries all these things. It's just my goofy drawing does not reflect that. But essentially, what we will have here is one extra vertex. I refer to it as V negative 1 because we stepped one left from 0. Name it any which way you like. The important thing to realize that nothing else changes fundamentally when it comes to the corresponding synthetic Euclidean planar geometry. Why is that? Because now with this vertex V sub minus 1, we draw the same line, we connect that point with Vn, and we have essentially and fundamentally exactly the same geometry, except that because that line segment of unit length 1, you see it contributes 0 for the sine. This line segment projected onto the perpendicular straight line, the vertical that houses all our sines, will produce 0. And when that line segment is produced on the horizontal straight line, it will produce exactly 1. And this is the, in some sense, extremal case, if you will, when angle is equal 0, cosine of 0 is 1. That's it, game over. We connect the points Vn and V1, and we do exactly the same thing. For our sums, I recorded them over here, and this time, let's be careful over here. I'll say 0. So we run the coefficient k with, not coefficient, the summation variable k from 0. Then for the cosine and sine, it will be exactly the same base of the isosceles triangle v minus 1, 0, vn. This guy projected horizontally gives us the sum of cosines where the summation begins with 0. And the same thing projected vertically will give us the sum of sines where summation variable k runs from 0. That's it. The rest from this formula follows the same. Here, we need to be careful. The angle that this straight line, our horizontal that houses the cosines, the angle that this line forms with this line segment v minus 1 vn is what? Well, it is some unknown angle. We call it x. But this time, look at this. It subtends which circular arc? V0, not, where was it? V1 as in the previous case, but V0 here and into here. So our circular arc is Vn to V0. And how many copies I showed over here of angle theta it carries? N, exactly. So twice the angle in the circumference by the corresponding theorem in plane geometry is equal to what? The corresponding central angle. So what is the central angle? V0 O Vn and theta. This is what I wrote for you guys over here. 2x equals to n theta, from where it follows that x is equal to n theta over 2. Game over. So cosine and sine percolate into our formula as n theta over 2, n theta over 2, n theta over 2. And what is going on with the length of the line segment Vn, V minus 1 Vn for this line segment from here to here? Again, essentially, fundamentally the same thing. This triangle is still isosceles. Its vertex is still O. The length of the sides that make this triangle isosceles is R. And what is the angle here? This time, it's the entire angle over here. Okay, I'm going to mess things up here. You see from here. And how many angles here? Not n, but n plus 1. Because we now roll our sum with the summation variable k equals 0. We have not n, but n plus 1. So n plus 1 terms. So here we go. 2r times sine of n plus 1 over 2 theta is equal to the length of the line segment Vn v minus 1, because again we bisect how many copies? n plus 1. N plus 1 copies of the angle theta we bisect. This is why 2 comes out, and 2 copies of 2 are projected onto this thing give us the entire base v minus 1n. This is what's recorded over here. And what's 2r? Same thing, nothing changes, the same isosceles triangle. Pick any one, and from any of these isosceles triangle, the smaller one, the small pizza slices, if you will, the angle theta, 1/2 of the angle theta, the angle bisector will be theta over 2. So the same relation will come over here. So let's say 2r times sine of theta over 2 is still 1. So 2r, 2r, 2r from here we put over here, and this is what we get. Game over. So for the corresponding trigonometric sums where the summation variable rolls with 0 and 0, we get the similar expressions, but again, idea is the same. We now explain the 2's. The 2's corresponds to the angular bisectors of the respective isosceles triangles, which dwell on the circle generated by a circle, which houses the vertices of our helper right triangles with the corresponding angles. This is the 1/2 everywhere, actually everywhere in all the cases. And the structure of these two sums is peculiar. Why? Well, because now we see the geometry. This ratio, why is it one and the same? Well, because we multiply one and the same line segment by the cosine in the first case and by the sine in the second. Boom, game over, we're done. To some people who think that a geometric explanation works for them, well, there you go. So we now have perhaps the best of both worlds. We have two analytic solutions that shuffle symbols just straightforwardly without thinking about the underlying geometry. And now we have a geometric explanation or a geometric motivation for why these formulas must look that way. And in some sense, behind these terms that make up that formula, we see what is the geometric backing, what is the geometric material behind this. Lastly, as a final step, it will take us a few seconds, we will now throw into the original sums. Remember, we had, let me pick which one, red, for example. We will throw a plus and a plus k theta. So now, instead of rolling our sum with the angle that is 0, we'll roll it with the initial angle that is a, because this is a geometric interpretation of the constant real number a. It's the initial angle that our unit line segment will form with the perceived horizontal. So in some sense, the first angle here will be not theta, but we will begin it with a, because the first term that corresponds to k equals 0 will kill the k times theta. 0 times theta is 0. So the first term here will be a. But again, as a heads up, for those who are curious, fundamentally nothing changes geometrically when we step into this situation. And here I will erase this picture, guys, and I will put a small number of triangles together to explain how things work. But fundamentally and essentially, the geometry of the underlying geometry of the sums when a is not 0 will actually be one and the same. Finally, when we bring the constant real number a into the mix, one possible geometric interpretation of this purely originally algebraic number, if you will, is the following. It is the initial angle which the line segment of length 1, this guy, remember our green line segments of length 1, makes with the perceived horizontal, and that corresponds to k in our sums. K in our sums equal to 0, the initial value k equals 0, k equals 0. Then in this case, we construct exactly the same triangles. It is these triangles here. See this triangle, and this triangle, and this triangle. We tile them up in exactly the same way, but remember this. If we produce the line that defines the hypotenuse of our right triangle initially into this straight line, and then again we construct a straight line that is parallel to the original side of our first right triangle, then the angle that this extended hypotenuse will make with this straight line that is parallel to our baseline with the horizontal will be A. And what do? Well, we prime our little engine that could as follows. With respect to this extended line, we incline the next hypotenuse by the angle theta. So what will be this angle over here? Well, I showed it in red, A plus theta. Correspondingly, the bottom line segment will represent what? The second term in our sum, cosine of A plus 1 times theta. And the vertical line segment, this one right here, will represent the sine of A plus 1 copy of theta here in this term when k is equal to 1, k is equal to 1, k is equal to 1, k is equal to 0, bam, bam, k is equal to 1, bam, bam, k is equal to 2. Again, with respect to this one, now carefully, we can produce this, extend this straight line, and with respect to that one, we incline the next one, what, by angle theta. So what will be the next angle here, the interior angle over here? A plus 2 times theta, and over here it's 1 plus 1 times theta. So here, this line segment, the horizontal line segment, will represent cosine of A plus 2 times theta. The vertical line segment, as I depicted over here, will represent sine of A plus 2 of theta. That will be our already third term corresponding to k equals 2. K equals 2, k equals 2. And this is it. This is how we keep piling these triangles one on top of the other. We project everything orthogonally, horizontally, vertically. Exactly the same picture remains. In some sense, I could have reused the previous. Drawing more or less, but instead of the first angle being theta, I should have marked it as A. But that drawing, as you guys saw, is too messy. Here you realize the same thing going on. So we have the underlying circle again that houses our vertices. Again, by the same reasoning, these 3 points and 2 sides of a triangle already determine the center. Perpendicular bisector of one, perpendicular bisector of the other. We bring in the other one. This perpendicular bisector of this line segment of length 1 with this one will point to the same point. This is the center of the circle. And then the rest of the features of a circle, properties of a circle remain. Look at this. We connect the first point v minus 1 with vn, this straight line. I already used by hand. I did not use the ruler. But what is the angle that this line segment vn, v minus 1 forms with the horizontal? A plus x. And what is x? Carefully now. X is the angle in the circumference that subtends, let's use, for example, I don't know, orange. X for orange, which circular arc? This one right here. See, this one. It's again one vertex less than the total number of vertices that we need when we construct our triangles. One less, so we're being careful over here. The total number of angles of magnitude theta will be, in this case, how many? N plus 1. And when it's one less, I showed over here, it's n theta. So by the corresponding theorem, twice the angle in the circumference is equal to the central angle, the corresponding central angle that subtends the same arc. What central angle subtends the arc from Vn to over here to V1, let's say? Well, it's this one, and it's n theta. So this is what I wrote. 2x equals to n theta, from where it follows that x is equal to n theta over 2. We understand that. And then we remember that these sums represent what? This line segment Vn, V1 times the cosine of that angle, n theta over 2 for the cosines. And that same line segment, the length of the same line segment, times the sine of this angle produces what? The sum of sines, produce the sum of sines. So then for the angle, for the line segment v minus 1 vn, in terms of the radius of the circle that houses our vertices, what do we have again? The same isosceles triangle, here, here, to here. And from this isosceles triangle, we now bisect all the angles, of which they're n plus 1 theta. We get this, n plus 1 over 2 theta. And this is the straightforward fact that this triangle is isosceles again. This is what we have. And then for the length of the radius, again, we have 2r times sine of theta over 2 equals 1. What is 1 over here? What is this 1? Well, this is the length of our hypotenuse, remember. And the triangle v minus 1 o v1 is still isosceles. So bisect the angle theta, get theta over 2. 2r times sine of theta over 2 gives us this line segment of length 1. Boom, game over. From here, we have our expression and game over. Remember that we said earlier, our original base times cosine of a plus n theta over 2 this way gives us this, gives us the cosine, this guy right here, sum of cosines. And this line segment times sine of a plus n theta over 2, this guy, gives us the sum of sines, shown in red over here. Game over. Cosines in green, sines in orange. But the formulas that we obtained now, look at this. They are exactly the same as the formulas that we obtained in the previous two segments. In the first segments, using the middle school arithmetic of basic popular trigonometric identities, and the fact that we morphed our sum into a sum that was telescopic. In the second segment, we used the basic arithmetic of complex numbers. And now we use the machinery of synthetic Euclidean plane geometry, because no coordinates, just a regular book one. Euclid's Elements, book 1, book 3, wisdom, and nothing else. And look, we obtained exactly the same formulas as we did before, which evidently shows that we did not make any mistakes. We were correct in all three deductions. It validates our reasoning for the most part in all of our episodes. The structure of both sums is the same, but when we were shuffling symbols somewhat, let's say analytically, without understanding of the underlying geometry, we looked at these formulas and we said, look at that. The ratio is the same, ratio is the same. Here's the cosine, here's the sine. Why is that? Well, the symbols, the symbolic shuffling said so, on the one hand. On the other hand, it is a rare case where we could come up with the reasonably straightforward geometric representation, and now we can, in some sense, read the geometry off of these results in a transparent fashion. This ratio is the length of this line segment. This ratio is the length of the same line segment. And the sine and cosine correspondingly project this line segment onto a horizontal for cosines, on the vertical for sines. Game over. Now, some of our viewers perhaps will say, Roman, why did you do all this elaborate dance with k equals 1? Then you stepped back with k equals 0, and as the last step, you gave us this guy, a. Why didn't you start with this one? Well, that is a valid point. This perhaps could have been done, but in my years of writing, for example, on Quora, I realized that the international audience is very broad. It's very difficult to figure out who knows what. Different people come from different backgrounds with different level of maturity in mathematics, with different level of skill. So to produce some sort of baseline that will make the majority, or hopefully all of our viewers, happy, I started with the simple case where k rose with 1. We have to deal only with one angle theta. This is straightforward arithmetic. We understand how it works. We complexified it a little bit by throwing k equals 0, added one line segment of length 1, and as a last step, we throw a. But look at how quickly. This is literally several seconds. Once you understand what is going on, these deductions over here will literally take you seconds, small 2-3 minutes, no more, because pretty much this is exactly the same case as we had originally when we started with investigating the sums when they rolled with 1, not with 0, but with 1. And coming back to my original comment, this is also, we learned that in theoretical physics we see it all the time, and in mathematics evidently too. When we create even a model that we ourselves qualify as crude, it's not very precise, it's a crude model. Still, sometimes even a crude model affords us a quite deep and meaningful description and understanding of the underlying material or of the underlying phenomenon. And I hope this was the case with this particular example. Again, this is the first time when we fixed one problem where we tasked ourselves with evaluating these two sums. I started with this one, but this is just a conversation starter. Obviously, we come to this guy too, and we produced the same one and the same result in three distinct enough ways. If you guys have more distinct enough ways, I personally would like to hear from you. Don't be shy, use comments, share your ideas with us and with our community. Meanwhile, this is it for the mathematical problem S3M4, and we will move on to a new challenge, the challenge in physics next. Before we jump to our next problem, which will be a problem in physics, I want to make sure that I button up the problem in mathematics that we dealt with in this episode. I honestly do not really remember if I mentioned it or not, but remember the lemma 1, the useful lemma that we proved at the beginning of this episode. How does it dovetail into this deduction? Well, we need this lemma 1 that we proved to show that when we incline all the unit length hypotenuses of our right triangles by angle theta with respect to each other, which is exactly what we do all the time, whether we roll k with 0 or 1 and whether a is 0 or not 0, we do that all the time. Then once we have this angle, remember the basic lines produced, we claim that the corresponding central angle that subtends this hypotenuse is over here. This hypotenuse is theta. Theta, theta, theta. This is where we need this lemma 1. So I'm not sure if I didn't mention it. I apologize, but this is where we need this lemma. Now, coming back to our physics problem, the next challenge will be the problem in physics. Remember, P stands for physics, CS for computer science, M for math. So in season 3, this is our first problem in physics. Consequently, S3P1. All this will be reflected in season guide. You guys, the other thing I want to mention all the time, I keep forgetting, do not neglect the season guides, the free PDF files that I have in my free GitHub repo. They will help you get around on work through the material that we present on this channel. They're quite helpful, where I index problems with their links. So in other words, you can search for the problem number, and then I provide the link. You can jump to the episode in which we solve this problem and in the episode in which we formulate it. So here, physics problem number 1 for season number 3, something very straightforward, but on the other hand, elegant, tasty, and not exactly exquisite, but already a little bit. So in this problem, we have 3-point masses M, M, M positioned at the vertices of an equilateral triangle. Here I designated the angles. I tried to put the arrows to show that the angular measure of the interior angle here is 60 degrees, here 60 degrees, and here 60 degrees as well. 60, 60, 60. Equilateral triangle, M, 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 3-point masses, all identical amount of mass, M, M, M. These 3 points are also 3-point masses are connected with ideal springs in such a way that pairwise, this is how they're connected. This M connected to this M with an ideal spring with the spring constant K. This point mass connected to this point mass with another ideal spring, exactly the same with the constant K, and the top mass connected with the leftmost mass with an ideal spring of constant K, the constant K. The whole contraption is positioned, let's say, in the horizontal plane. there is no friction in the system. So when the point masses, all 3 point masses begin moving, we neglect the friction. Obviously, we neglect the gravitational interaction between the 3 masses as a whole, and with the masses built into the springs themselves. We say, let's say, the point masses are themselves much heavier than the springs, and the distances between the point masses are basically, when it comes to gravitational interaction, we neglect them. They do not really interest us. So what happens next is the following. Originally, the system sits on the horizontal plane in the steady state. Nothing is happening, and then somehow all 3 masses, for example, pulled away radially with respect to, let's say, the center, the corresponding center of the circumcircle of this triangle. Radially means away from the center. This pulled this mass pulled this way, this mass is pulled this way, and this mass is pulled that way by exactly the same amount. Everything is symmetrical, everything is ideal, uniform. All 3 masses are pulled away from the center radially by the same amount, let's say. And also all 3 masses are let go also at the same time. So what happens then is that our little system begins executing the so-called simple harmonic oscillation. The system begins oscillating as a whole in a certain way, again in the horizontal plane. And the question over here is this: neglecting friction in this case, find the frequency of this simple harmonic oscillation of the system as a whole. Now, this system as a whole, one more time, executes simple harmonic oscillation. That means that the amplitudes are small enough. All the laws that you know about how this ideal springs with the constant k work, they apply. And now the system gently executes the simple harmonic oscillation, and we want to know the frequency, omega. What is the frequency of these oscillation of the system as a whole, or symmetric oscillations, if you will? See what's going on over here, if you can come up with a plausible explanation. Again, we want to hear your story, because in physics, just like in mathematics, is the same thing. For the most part, nobody cares about the solutions of all these problems, but what everyone in the physics community cares about deeply is about your ability to produce a convincing story behind your line of reasoning. Like, why is the answer, for example, it is what it is? So find omega. Remember also that in this simple case, omega t is equals to 2 pi. T is a period of oscillation. So if somehow you can invent the way to compute the period of oscillation of this simple harmonic oscillator, triangular oscillator, then you know the frequency. And if you know the frequency, you know the period. This is just a helpful hint for you to see what is going on. Try again also to solve this problem in as many ways as you can see, different ways as you can master. And this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share a couple of my solutions of the physics problem S3P1.